Okay, so our next topic is higher order derivatives. And I want to do a bit of calculations just to see that we're not scared of them. They're not scary. Of course, we're discussing partial derivatives of functions of several variables. And there's one important theorem that's going to show up in a minute. Okay, so let's start with an example. So I'm going to look at the function. It's going to be a function of 3 variables. And it's given by e to the power x times y plus z cosine of x. So this is a scalar function of 3 variables. And I want to start calculating partial derivatives. So what's the derivative of f with respect to x? The derivative of f with respect to x, I just regard all the other variables, y and z, as fixed, and take derivatives with respect to x, right? We all know how to do that. So what do I get? I get e to the xy. The derivative of e to the something is always e to the something, times the inner derivative. What's the inner derivative? Y. Do you agree? X is the variable, y is now a constant, fixed. Plus, what's the derivative of this with respect to x? Z is fixed. The derivative of cosine minus sine. I'm just going to change this to a minus. Does everybody agree? Good? What is the derivative? So notice that what I get, we mentioned and emphasized this several times, the derivative of a 3-variable function with respect to x is again a 3-variable function, right? It's again a function of y, x, and z. Do you see that? So now I can ask, what is the derivative with respect to x of this new function? Sorry, of df to dx. The derivative with respect to x of the derivative with respect to x of f. Do you agree that this compiles, that this makes sense to ask this question? And there's notation for it. The notation is d squared of f divided by, this is the notation, dx squared. And sometimes you even omit this. In fact, you write like this. Okay, this is just notation, short for writing this. Okay, so what is it? What is it? I have to take the derivative of this with respect to x. So y is fixed, e to the xy is e to the xy, and again there's that other y from the inner derivative, so I get y squared, right? Minus z, the derivative of sine, is cosine. Does everybody agree to this? Okay. But now I can ask, what's the derivative of this function, the derivative of the partial with respect to x, with respect to y? That also makes sense. So I can ask, what is d to dy of df to dx? And the notation for this is d squared f over dy dx. Okay? What is it? I'm looking at this and taking the derivative with respect to y. Okay? So here I have a product. So I'm doing the product rule. So I get 1 times e to the xy plus y times the derivative of this, which is e to the xy, times the inner derivative with respect to y, which is x. Did everybody follow this? And what's the derivative of this with respect to y? 0. No y is there. Good?
How can we know that we have to do before the derivative with respect to x and then to y? Or
that's the notation. You take this and take its derivative with respect to y. And when it's written like this, you first do the x and then do the y. This is your clue how to remember this. Okay? This is what we call Leibniz notation. Okay? And we're going to see that it gets confusing when we discuss the other notation. I'll do it in a minute. Okay? One more second order partial derivative for this is taking the derivative of this with respect to z. Right? What's the derivative of df to dx with respect to z? I'm out of space. Let's do it here. The derivative with respect to z of df to dx, which can be written as d squared f over x. And what is it? What do we get? This is z-less. No z's here. So we just get minus sine of x. Does everybody agree? So how many more partial derivatives of order 2 can we calculate for this function? 6, exactly. Because I can take the derivative of f with respect to y and then calculate its 3 partial derivative with respect to the 3 variables. And likewise, I can take the derivative of f with respect to z and calculate its 3 partial derivatives with respect to the 3 variables. Right? Let's do that, but I'm going to do it a bit more quickly. Okay, a bit more quickly. So, the derivative of f with respect to y, let's write what y is, what f is up here, so we don't forget. So it was e to the xy plus z cosine of x. So the derivative of f with respect to y is x e to the xy. That's it, because this does not have y's in it. What's the derivative d squared of f with respect to dy squared? So the derivative of this, again with respect to y. So it's x times e to the xy times the inner derivative. So we get x squared. Do you agree? Okay, make sure I don't make any mistakes here. It could get a bit confusing. You have to remember which variable is the variable with respect to which you're taking the derivative. Okay? What is d squared f to dx dy? First with respect to dy, then the derivative of that with respect to x. So now I'm taking the derivative with respect to x of this thing. So it's e to the xy plus x e to the xy times the inner derivative. So there's a y here. Do you agree? And finally, the derivative of f, now with respect to z, there's no z's here, right? So it's 0. Everybody with me? If anybody's sitting here and looking at your eyes, I can see some of those looks of, oh boy, this is way too fast for me, what is he doing? Then catch up. It's very important to take derivatives very, very easily, okay? And it's just a matter of practice. There's nothing more to it, okay? So the derivative, so 3 more. The derivative of f with respect to z is just cosine x, right? These are easy. So the derivative of that with respect to z, denoted like this, is 0. The derivative of that with respect to x is minus sine of x. And the derivative of that, the second order derivative with respect to y, is 0 again. Do you agree? Everybody good? Okay. So now I want to focus your attention on something that you may have noticed. We have these specific second order derivatives, partial derivatives, which are with respect to 2 different variables. They're nicknamed mixed partials. Okay, mixed partials, because there are 2 different variables here. And notice that if we take the derivative with respect to z, and then take its derivative with respect to x, what did we get? Minus sine of x. That's the same thing that we got, look back at this board a second, when we took first the derivative with respect to x, and then took its derivative with respect to z. We got the same thing. Good? And that happens with all the mixed partials. Look at the derivative of f with respect to x and then with respect to y. We got e to the xy plus xy e to the xy. And then look back on this board. First the derivative with respect to y and then with respect to x. We got the same thing. Right? And the third mixed partial with y and z, we got 0 here and we got 0 here. Okay? So this is not a coincidence. This is a theorem. So let's write that. Theorem. But as with many theorems, it has conditions that have to be satisfied for the theorem to hold. And the conditions are basically that everything is nice and smooth. Okay? So if fxy, or in general, it could be stated for, let's state it for fxy and say what it is for fxyz, belongs to C2. C2 means that it has all the second order partial derivatives and they're all continuous. Okay? C1 was having all the first order partial derivatives continuous. C2 means continuous second order partial derivatives. Okay? That's the assumption. Then the derivative of f with respect to x and y is the same, whether you first take the derivative with respect to x and then with respect to y, or vice versa. So the mixed partials are equal. Good? Everybody? Okay, so that's what we saw happening in the example for all the, so let's just say that if f is a function of x, y, and z, then the then part of the statement is going to have 3 equalities for all the various mixed partials. Clear? Good? Do I have to write the f, x, y, z version of this theorem, or is it clear what's going to be written there? Everybody? Okay. Remarks. So first of all, notation. Notation. So we already know that the derivative of f with respect to x can also be written as f prime sub x, or even just f sub x. Right? We've seen that. So similarly, along that same line, the derivative of f with respect to the second order partial with respect to x twice can be written as fxx prime prime, or simply fxx. Okay? And now here comes the confusing part. I hope I don't get confused. So the derivative of f with respect to x and y, so what was this? This was taking the derivative of f with respect to y and taking its derivative with respect to x. That's why this is the order in which it's written, in order to hint at this, right? So that's going to be written as f y, and then I'm taking its derivative with respect to x. Or in short, f y x prime prime, or just f y x. Okay? And the reason that it's confusing is that notice that in this notation you write the y first and the x second, whereas in this notation you write the x first and the y second, when you mean the same thing. And the only reason for this theorem is so that we don't get confused in these things. It doesn't matter because of the theorem. It tells you that if you got confused, you get the same thing anyway, right? That was a joke. That's not the reason for the theorem, of course. But the theorem tells you that if there's, You have to be very precise in mathematics, right? You can't just get confused in things like this. But in this specific case, usually it's not too harmful if you get confused because of the theorem. They're the same, whether you write it in this order or the other. Clear? Okay. So these are the two notations. I'm usually going to use either this without the little primes, either this or this. These are the two that I'm going to frequently use. Okay, clear? Questions? Everybody good? Okay. Another remark is that I want to give you a couple of examples. I'm not going to work these examples out because it takes a bit of calculation, okay? Because you have to check carefully at cases, and so I'm not going to work them out. I just want to give you examples for you to practice on in which the theorem doesn't hold. And you can ask, what do you mean the theorem doesn't hold? It's a theorem. It has to hold always. Well, it only holds if the conditions of the theorem are satisfied. If the function is not C2, then it doesn't have to hold, and in fact, it doesn't always hold. So here's the first example. So the first example is the function, sorry, I forgot to write fxy. fxy equals x cubed divided by x squared plus y squared. This is at xy, which are not the origin, and 0 at the origin. And this function, you can check, and I'm leaving it as an exercise. So EX stands for both example and exercise. It's very convenient. So I'm leaving it as an exercise that one of the partials, one of the second order partials doesn't exist. At 0. And in particular, they're not equal because the other one does exist. Okay? So let's write that. And thus, the theorem doesn't hold. Because the other one does exist. And why? How can the theorem not hold? Well, if it doesn't exist, it of course can't be continuous, right? And therefore the conditions of the theorem are not satisfied. Clear? And the other example for you to try is the function f of xy equals xy times x squared minus y squared divided by x squared plus y squared, and 0. This is when we're not at the origin, and this is at the origin. And in this case, all the second order partials exist at 0, but they're not equal. And the reason is that they're not continuous. Okay, so all second order partials, please do this, verify this, it's good practice, exist at the origin, right? Since we're checking at the origin, you can see that in order to calculate partials, you have to resort to the definition of partial derivatives, right? Do you know what I'm talking about? Okay, you can't just do product or quotient rules. You have to resort to the definition because we're talking at this point. Clear? So that's why it's a bit of work. So all second order partials exist at 0, 0, but are not continuous. Are not all continuous. And the mixed partials are not equal. So the theorem doesn't hold because the function is not C2, because the second order partials are not all continuous. And you can see that it doesn't hold because you calculate the mixed partials, you get values for both, but they're not the same value. Okay, so these are examples. Okay, Okay. Let's look once again at this theorem here, and actually I want to maybe take a step back and discuss higher order partial derivatives in general. Those are very, 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 very important in applications. We don't have the time in this course to do a physics course and to show you all the various phenomena in nature that are modeled by partial differential equations, by second or in particular by second order partial derivatives. But for example, the heat equation and the wave equation and the Laplace equation and the Poisson equation and many, many things that you'll learn about in physics and hear about are all equations super important in various subjects that are all just equations about partial derivatives, namely of order 2. Okay, and so maybe you'll see this. You will see this along your future studies. This theorem that says that the mixed partials are equal was probably proved first by a mathematician called Clairaut, and usually is attributed to Euler. Euler is a very famous mathematician in the 18th century. He, for example, invented a lot of the notation that you know, like the sigma notation for summation is Euler, and the I notation for complex numbers is Euler, and E, you know, little e from e to the x, that's E for Euler. Okay, so he's an important guy. The theorem is also attributed to him. So how could a theorem be attributed to several different people? It depends on the rigor in which it was proved. And so maybe somebody said, this looks correct, but his proof was not in modern day standards, the way we consider a full proof, but he's nevertheless used it and people started using it, so he gets credit for the theorem. The most up-to-date standard, the proof with up-to-date standards of the theorem was given by a mathematician named Schwarz in 1873, which is not that long ago. And so in some places you'll see this called the Schwarz theorem. Okay? So that's it about higher order derivatives. We're going to use them a lot. In particular, we're going to use them very soon when we discuss Taylor polynomials for functions of several variables. So there we're going to need higher order derivatives. We're going to use them when we study minima and maxima of functions. Even in Calc 1, how did you classify minima and maxima? You use the second derivative test, right? To see if it's a minimum or a maximum. There's going to be an analog here that's going to use second order partial derivatives. So these things are important, and we'll discuss them a lot as we progress.